All right, welcome back. In this lecture, we're going to cover section 2.7 on the normal distribution. This is a very important distribution. There are many real-world phenomena that follow a normal distribution, and this is probably the distribution that we use most often in statistics, or at least in an introductory statistics course. So let's get to it. Unlike the binomial distribution, which is discrete, the normal distribution is continuous, and it's defined by this PDF right here, this function. So a function that has, or a distribution that has this as its probability density function would be a normal distribution. And before you get scared thinking that we're going to be doing a lot of work with this function, don't worry, we're not going to be working with the function itself. We'll use the Desmos graphing calculator to calculate normal probabilities. But the reason that I put this on here is to emphasize that the mean, mu, and the standard deviation, sigma, show up in the formula for this distribution. In fact, those are the only two, those two values, the mean and the standard deviation, uniquely determine the way that our distribution is going to look. They uniquely determine the way the graph is going to look. And so that's why we spent so much time in Unit 1 talking about means and standard deviations, right? Because they're going to continue to pop up all semester. They're as I said, they uniquely determine the shape of a normal distribution. In particular, here's what mu and sigma do. So the highest point on our graph occurs at x equals mu. So if you have a case where mu equals 0, right, then the highest point is going to be here, okay? If you have a case where mu equals 3, okay, then the highest point is going to be here at 3. The standard deviation, on the other hand, as we know, it determines the spread of a distribution. It determines how spread out the distribution is. So this blue distribution here is when we have a standard deviation of 2, and this pink one is where we have a standard deviation of 1. So you can see the one with the larger standard deviation is more spread out. Okay, they both have the same center, 0. Okay, but the blue one is more spread out. So that's how the normal distribution works. It's the same bell-shaped distribution. We're just going to call bell-shaped distributions normal distributions now. They're not exactly synonymous, but that's kind of the idea, is that you're going to have a bell-shaped distribution when you're looking at a normal distribution. Let's talk about computing probabilities. Now, if you had to do this by hand, okay, you may recall that if f of x is the PDF of a continuous random variable, then this is how we compute probabilities. We talked about this briefly in 2.5, okay? But of course, we're not doing any of those kinds of calculations because they require calculus. And most of you have not had calculus. But just for your information, for you calculus nerds out there, we would replace f of x with the PDF of a normal distribution, and this is the probability that we would have to compute if we wanted to do this by hand. Note that for those of you who have had calculus, that even with calculus, this would be a pain in the butt, right? So even if you know calculus, that computation is not easy. So we're not going to be doing it by hand. What I would like for you to understand is this, that the probability that x is within a certain interval, let's say between a and b, that probability is equal to the area between the curve and the x-axis, right, over the interval. So probability corresponds to area. So the probability x is between a and b is just this area right here, right? Okay. Here's how we do this in Desmos. So this is similar to the way the binomial distribution works in Desmos. We open up the Desmos graphing calculator, and then we're going to type in, instead of binomial dist, we're going to type in normal dist. And of course, we're not going to type in literally the Greek letter mu. We're going to type in whatever the mean of the distribution is, and instead of sigma, of course, whatever the standard deviation is. And then we'll follow the same, well, similar steps to what we did when we were computing binomial probabilities. So let's just take a look at some examples. Number 1 here says, the weights of giraffes are approximately normally distributed with mean mu equals 2,200 pounds and standard deviation or sigma equals 200 pounds. Compute the following probabilities and draw a picture of each. See, so for part A, we want the probability that x is between 2,400 and 2,500. It'll be easier to draw the picture once we do the calculation in Desmos, but we can get a decent looking picture now. So let's just draw a quick picture of this. So you give yourself a little bell-shaped distribution. Do your best, okay? Mine's not perfect, so yours obviously doesn't have to be. But the mean should be right in the center of the distribution. And the mean in this case is 2,200 pounds. So 2,200 should be right about here. Okay, and then one standard deviation is 200 pounds. So if I'm one standard deviation above the mean, then I'm at 2,400. And if I'm two standard deviations above, then I'm at 2,600, and so forth. Now, we're interested in knowing the probability that x is between 2,400 and 2,500. So that would be roughly this area right here, okay? Between 24 and 2,500. Okay, that's that area. Let's head over to the Desmos calculator and see how we compute this. So in the Desmos calculator, we're going to type normal dist. Okay. And then we can put in whatever the value of the mean was. I think it was 2,200. Yes, the mean was 2,200 and the standard deviation was 200. So we'll put in 2,200 for the mean, and then comma, and then 200 for the standard deviation. Okay. And you'll notice that the graph that you're getting over on the right is not super great. But if you zoom in, so click the little magnifying glass with the plus sign. Okay, now you get this normal distribution, right? It zooms in on the right spot. And if we want to compute probabilities, then we would click on the little button that says find cumulative probability, okay? We're looking for notice that it gives you the mean and the standard deviations and everything along the x-axis, just like what we wrote out a second ago. We want the probability that x is between 2,400 and 2,500. So I'm going to click on the minimum and put in 2,400. Click on the maximum, put in 2,500. And there you go. So looks like that's about 0.0918. Okay, we'll typically round to 4 decimal places. So say this is about 0.0918. Is that what I said? Yes. Okay. So let's look at the next one, right? Part B asks for the probability x is less than or equal to 2,100. Okay. So this time, here's 2,200. One standard deviation below the mean would put us at 2,000, okay? Because the standard deviation is 200. So 2,200 minus 200 is 2,000. And we're looking for the probability that x is less than 2,100. So 2,100 would be right in between 2,200 and 2,000. We're looking for this probability right here. Okay. So this is probability that x is less than or equal to 2,100. Let's take a look. So since we want the probability x is less than or equal to 2100, there is no lower bound. We would just type in negative infinity. Okay, but the maximum should be, the maximum should be 2100. Okay, and there you go. It's shading in the correct region. So it looks like that probability is 0.3085. Okay. I'm going to box my answers. Part C is looking for the probability x is greater than or equal to 2100. Well, that's just going to be kind of the mirror image of what we did in part B, right? We have 2200, 2000, and 2100 would be right in the middle. But this time we're looking for the probability x is greater than this, right? So this is probability x is greater than or equal to 2100. And let's see what we get. So this time there's no upper bound, right? The upper bound, we would just type in infinity. So that comes out to 0.6915-ish. Okay, so that's how these probabilities work. Now, of course, for the purposes of showing your work, what I would like for you to do on, let's just use part A as an example. I'd like you to write down what distribution you're using. In our case, we're using the normal dist, okay? And then, write down what you put in for the mean and what you put in for the standard deviation, okay? And then also tell me on each problem what you put in for the minimum and maximum values, right? So for the minimum here, we put in 2400, right? For the maximum, we put in 2500. And then when you're giving your answer, right, write out the full probability statement. Don't just write down the probability itself. Don't just write down the number, the answer, but give me the full statement and say this is approximately 0.0918. Okay, and that's what I want to see. Similarly for the rest of them, like on part B and C, you wouldn't have to rewrite this first part, okay, because we're working with the same distribution, so you don't have to rewrite it. But you could maybe say what you put in for your minimum value, we put in negative infinity, and for our maximum value, right, we put in 2100, and then we got our answer. So anyway, I won't go back and rehash all of that, other than to just say, please show your work. It's in your best interest to do so. I can't give you partial credit if all you do is write down your answer and it's wrong. So let's look at a few more examples. I need to mention this. This is very important. But you may note that with discrete distributions like the binomial, we could always compute the probability of x being a particular value, right? Like the probability x equals 2. But with continuous distributions like the normal, we can't do this, right? With continuous distributions, the probability of observing one particular value is always 0. It's always 0. The reason for this is because since x is continuous, there will be infinitely many possibilities, okay? And so the probability that x equals one particular possibility is going to be 1 over infinity, basically. It's going to be 1 over n, but as n goes to infinity. And if you think about what happens to the number 1 over n, as n gets really large, it's going to go to 0, right? 1/2 is a bigger number than 1/10, which is a bigger number than 1/100th, which is a bigger number than 1/1,000,000th, right? So as n gets large, 1 over n gets really close to 0. So for a continuous distribution, the probability that x equals something is always 0. And that ends up making a big difference in the way that we work with probabilities in in the binomial calculator versus the normal calculator, or more generally for discrete distributions versus continuous distributions. So let me just walk you through this, right? In a continuous distribution, since probability x equals a is always 0, the probability that x is greater than or equal to a would be exactly the same thing as the probability that x is greater than a, because the equals doesn't contribute anything, right? And similarly, the probability that x is less than or equal to a would be equal to the probability x is strictly less than a, because the equals a part doesn't contribute anything. So notice the difference, right? Notice the difference, and that's kind of laid out in this chart. This is just an example, but I think it serves the purpose, right? If you're dealing with a binomial distribution or any other discrete distribution, then the probability x is strictly greater than 4 would be equal to the probability x is greater than or equal to 5. Okay, you have to go up one. If you're looking for the probability x is less than 4, then that would be equal to the probability x is less than or equal to 3. Okay, this is the case for a discrete distribution. But for a continuous distribution, okay, the probability that x is greater than 4 would be equal to the probability that x is greater than or equal to 4, right? You wouldn't change the number. And similarly, probability x is less than 4 would be equal to probability x is less than or equal to 4. You don't change the number. So with discrete distributions, you have to adjust the number when you're putting this into the Desmos calculator. For continuous distributions, you do not have to adjust the number. If any of this is confusing, I would encourage you to go back to the 2.6 notes, okay, and look at the examples where we worked out examples using the binomial calculator, and then contrast that with what I'm about to show you here, okay? So number 2 here says, a pedestrian obtains the heights of her 203-year-old female patients. The heights are approximately normally distributed, with mean 38.72 inches and standard deviation 3.17 inches. Determine the proportion of 3-year-old females that have a height, and then we're going to look at a whole bunch of different scenarios. In part A, we want the proportion of 3-year-old females that have a height of exactly 35 inches. So in other words, in part A, we're looking for the probability that x equals 35. Now we're told that these heights are approximately normal, and furthermore, we know that height is a continuous variable. So the probability x equals 35 is going to be 0, right? Just given our discussion above. If you wanted to, you could try to compute this in Desmos. So you could type in normal dist and put in the mean, right? The mean was 38.72. Put in the standard deviation, that was 3.17. And then for the minimum value, for your lower bound, you put in 35. And for the maximum value, your upper bound, you also put in 35. And if you do this, you'll see that this is exactly what you're going to get. In fact, let's head over to Desmos and make sure that that's what we get. 38.72. So 38.72 and 3.17. 0.17. And what value were we looking for? 35, was it? Yeah, 35. So probability x equals 35. We would put in 35 for the min, 35 for the max, and yeah, the probability is just 0. Here, let me zoom in. You notice that it's not highlighting anything, right? It's not even highlighting this 35, the bar on 35, because the width of that rectangle would just be 0, right? Okay. Part B asks for the probability that x is between 34.9 and 35.1. So we're going to do the same thing, right? This time we're looking for the probability x is between 34.9 and 35.1. And we're going to use the normal distribution again. This time our minimum value is going to be 34.9, and our maximum value is going to be 35.1. So we can't compute the probability x is exactly equal to 35, but we can find the probability x is between 34.9 and 35.1, right? So let's do that. So 34.9 and 35. Oh, come on. 35.1. There you go. And now you'll see that the graph is highlighting that little tiny sliver, and it looks like the probability of this occurring is 0.0126. Okay? Part C. What's the probability or what's the proportion of 3-year-old females that have a height that's at least 35 inches? By the way, I should mention now that probabilities and proportions are really the same thing. The probability that a 3-year-old female would be at least 35 inches is the same as the proportion of 3-year-old females who are more than 35 inches, right? Or at least 35 inches is what we're supposed to be looking for. So probability of being at least 35 inches means that you're 35 inches or taller. So x greater than or equal to 35 is what we want. So our minimum value is going to be 35, and we won't have an upper bound, right? It's just going to be infinity. Okay, let's see. 35. Infinity. So there's a 87.97% chance of this, right? 87.97% of 3-year-old females are more than 35 inches tall. Okay, so we say 0.8797. Okay, and then part D is asking for the probability that x is more than 35 inches. So we want probability x is strictly greater than 35 inches. If this were a discrete distribution, then we would say that this would be equal to the probability x is greater than or equal to 36. Okay, if this were discrete, but it's not discrete, it's continuous, right? For a continuous distribution, the probability that x is greater than 35 is exactly the same thing as the probability x is greater than or equal to 35. And we've already computed that probability, right? 0.8797. Okay. Part E. We want the probability that a 3-year-old girl is at most 37 inches tall. At most 37. So that would mean 37 inches or less, right? X less than or equal to 37. So we're not going to have a minimum value. We'll put in negative infinity for that. And for our maximum value, we'll put in 37. Let's see what we get. So negative in t. And the maximum value, 37. Okay, so it looks like that's 0.2937. Notice that it's highlighting the area to the left of 37, right? Which is exactly what we want. So 0.2937. Okay, and then finally, for part F, I think I intended this to say less than 37 inches. So I will change that in the notes before I post this video. So yours should say 37 because I wanted to make this point, right? I wanted to say probability x is strictly less than 37 for a continuous distribution is going to be equal to the probability x is less than or equal to 37. They're exactly the same thing. If this had been a discrete distribution, we would have to say that this is equal to probability x is less than or equal to 36, right? And take it down one. But this is continuous. So probability x is less than 37 is exactly the same thing as the probability x is less than or equal to 37. And we've already computed that value, right? 0.2937. Okay, so this is how normal probabilities work. Pretty straightforward. You're just going to use the calculator in Desmos to do this. Let's talk about the shape, center, and spread of a normal distribution. As far as the shape is concerned, the normal distribution is the quintessentially bell-shaped distribution, right? It's always bell-shaped by definition. The center of the distribution, so mu sub x is just going to be the mean, the mean of the distribution. Mu sub x equals mu. That's pretty obvious, right? Let me just emphasize that this is also the expected value of the distribution, right? So if x is a normal variable, then e of x is mu. Okay. This is very clear that this should be the case intuitively, but if you want a proof of it, you can watch this video right here. Okay. What you would have to do to prove it is perform this calculation where you replace f of x with this probability density function. And if you do that, then you do indeed end up with e of x equals mu. In a similar way, sigma sub x equals sigma. So the standard deviation of the distribution of our random variable x, if x is normally distributed, is just equal to the standard deviation of the distribution, right? Let me give you a couple examples of that. And then I think that's the end of the section. So let's just do a few of these. This example says, the following data represent the speeds in miles per hour of 16 randomly selected vehicles traveling down a state highway. Part A says to use Excel to compute the sample mean and sample standard deviation of the data, assuming that these statistics are good approximations for the population mean and standard deviation. If another car came traveling down the highway, how fast would you expect it to be going? Well, it's been a while since we've worked in Excel. If you want, you can open up Excel and then enter these values manually into the spreadsheet, and then you can use Excel to compute the mean and the standard deviation. I went ahead and did that already, so I'm just going to give you the answers. But in Excel, to compute the mean, the sample mean, x bar, we would use the equals average function. It's been a while since we've had to do this, right? And then we would select our data. And it turns out that this is approximately 60.6 miles per hour. And for the standard deviation, we would use standard deviation dot s for sample, select our data, and this comes out to about 5.4. Okay. Now, we're asked to assume that these statistics are good approximations for the population mean and standard deviation. In other words, we're asked to assume that mu is approximately the same thing as x bar, okay, which is approximately 60.6. So we're assuming that mu equals 60.6. And then the question is, if another car came traveling down the highway, how fast would you expect it to be going? In other words, compute the expected value. Well, the expected value is just equal to the mean, which we're assuming is approximately the same as the sample mean of 60.6. So if another car came randomly barreling down the highway, we'd expect it to be going about, maybe you would say something like 61 miles per hour or something like that. Okay? Part B says, using the values that you computed in Part A as approximations for mu and sigma, compute the probability that a car would be traveling down this highway at a speed faster than 57 miles per hour. So we want the probability that the speed of the car X is faster than 57 miles per hour. We're going to use the normal distribution for this. We'll put in the mean of 60.6 and the standard deviation of 5.4. Our minimum value will be 57, and our maximum value will be infinity, right? Because we're looking for the probability that X is greater than 57. Okay, let's see what we get. 60.6. Oh, hold on. 60.6 and 5.4. Oh, and I've forgotten the probability we're looking for. X greater than 57. Okay, there we go. Let me zoom in so we can see it. Yeah, so there's that distribution. Okay, so about 0.7475. Okay, and then one more. We're asked, would it be unusual for a car to travel down this highway at a speed exceeding 51 miles per hour or 45 miles per hour? Exceeding those values. We already know the answer to this question is going to be no. I must have wanted different numbers here. Let's change 45 to 71. So, would it be unusual for a car to travel down this highway at a speed exceeding 51 miles per hour? Or what about 71 miles per hour? Well, let's see. So, to answer that first question, my strategy for answering the question is that I want to compute the probability that the speed is more than 51 or more than 71. And if those probabilities are less than 5%, then I'll say that, yeah, that's unusual, okay? So we'll look for the probability X is more than 51. For that, my minimum value is going to be 51, and my maximum value is going to be infinity. We'll see what that probability is. And then we'll also look for the probability X is greater than 71. So here my min will be 71, and my max will be infinity. I'm not sure why I put a comma here and not anywhere else. Okay, let's see what we get for these probabilities. So 51. Okay, so that's 0.9623. And for 71, that comes out to 0.0271. So, would it be unusual for a car to travel down this highway at a speed exceeding 71 miles per hour? No, right? This is not unusual. In fact, it's highly likely that the car will be going more than 51 miles per hour. Is it unusual if it would be going more than 71 miles per hour? The answer there is yes, right? That's less than a 5% chance of that occurring. So no, it wouldn't be unusual for a car to exceed 51 miles per hour, but it would be unusual for a car to exceed 71 miles per hour, since probability x is greater than 71 is 0.0271. So it's like a little less than a 3% chance of happening, which is less than a 5% chance. And so we would consider it unusual. Okay, and so that's that. All right. We'll move on and talk about some more distributions in the next section, and I will check in with you then.